two particles here that we're considering for chapter 11, number 11. Now, if it was a uniform object, we would just use I times omega, because the moment of inertia is just going to be an implied sum of all of those point masses with their respective distances. So just use I. But if in this case, we just got two particles, we can just use mv times r. So mvr we know is the same thing as I omega. We know that I omega is best for so a rigid object, or object with specific geometry. And then MVR is the case with just point masses that we have. Point masses that we have in like in this system here. All right, so now we have our masses, 4 times 5 times 0.5, which is the distance of 4 kilograms, and they're both moving at tangential velocity of 5 meters per second. And that's because they have the same distance away from the center. If this is 0.6, this is 0.5, they would have different velocities. So 4 times 5 times 0.5 plus 3 times 5 times 0.5 gives us 17.5 kilogram meters squared per second. Those are the units of angular momentum. All right, and I just gave this other example just off the top of my head. Instead of just dealing with point particles, we deal with a sphere or a cylinder or some other disk or something, and then we can just use the moment of inertia of that object times the angular speed, and then we can get the angular momentum of that. It should be 90 kilograms meters squared per second. And then this is the problem. Okay, so today we're going to go to section 11.4. Section 11.3 we've pretty much looked at as far as getting an equation for torque. So if you're in your textbooks, skipping past section 11.3, we've derived the equation for angular momentum. And we know that net external torque, if the torques are not balanced, we get this equation for unbalanced torques. Like if a system is rotating with some angular acceleration, very similar to F equals ma. Point mass is the distribution of mass. One-way acceleration, this is a rotational acceleration. So these are analogs of each other, right? We dealt with that in chapter 10 and elsewhere. So getting up to section 11.4, we're now going to isolate our system, talk about conservation of angular momentum, very similar to conservation of linear momentum. Conservation of So we isolate it from the environment. We close it off from external forces like friction, air resistance, which is a form of friction. And we're looking at all of the torques within the system. Whereas in linear momentum, we're looking at all of the forces, internal forces. All of those forces together will net to zero. We're just not, they're not going to be a part of the explanation when we're talking about saving angular momentum. We know that the outside forces will be zero because we're closing it off. The outside forces will be summed to zero in linear momentum, but now in this case, we're going to have the outside torques in the system equals 0 as well. So if we have an object that's just spinning about, its center of mass, and it's just spinning, it has a moment of inertia I, it has omega, and it's just constant, well then the torque on that system is going to be 0, especially if it's just spinning with a constant angular momentum. Now, if we apply an external torque by the application of an outside force, then the angular momentum changes in a certain amount of time, but we're saving the momentum here. We're saving the angular momentum, so we are not going to consider any outside torques. So if we want to save angular momentum, so it can only be saved it's only equal to 0. So external torque, change in angular momentum per time is going to be equal to 0. Your external forces are very similar to when your external forces are going to be equal to 0 for saving linear momentum. So the outside torques are 0, much like the outside forces for linear momentum is going to be 0. So that's the only way we can save the rotational momentum, angular momentum of a system of 2 or more objects. So if I set a wheel spinning and let it spin uninterrupted, that's the case of a wheel spinning. Or if I push a mass, so like I had the case before, the wheel is just spinning about its center of mass with angular velocity I, moment of inertia, angular velocity omega, and moment of inertia I. It's just spinning about. The momentum is never going to change. If I have a point mass and I push it, it's going to be moving along at constant velocity, no outside force. It's going to keep on moving with that momentum. It will be constant. So, and if I encounter another wheel and it, say, provides an internal torque, if you will, on that other wheel and gets it spinning, then the momentum between both of those guys added together will be equal to 0. There will be no change. So the momentum that this guy had, and let's say the momentum of another wheel that it applies a torque to and gets it spinning, that momentum will be the same as the momentum in the beginning. Same thing with this point mass. If I have a point mass hit another mass, if it was at rest, and let's say that point mass at the same mass as this first guy, this mass would come to rest and the other guy would move off at the speed that the first mass had. So the momentum is always going to be constant. because there are no outside forces or outside torques here to mess up the momentum. So in order for the linear momentum to be constant, so like this total momentum is constant or saved, we also have the total angular momentum to be constant or saved as well. Therefore, whatever we had in the beginning will be the momentum in the end. For the linear case and the angular case. And that can only happen when outside forces is 0 and here if the outside torque is 0, saving the momentum. So I'll leave that here. So given those stipulations, now we already know MIVI equals MFVF. That's for the linear stuff. And so therefore, the angular momentum will be very similar. Moment of inertia times angular velocity, not linear, is going to be the same. The moment of inertia in the end times the angular velocity in the end. Linear momentum before equals linear momentum after, same with the angular momentum case. So this II is the initial moment of inertia. Omega I is the initial angular velocity. That. And so just to illustrate, like say for instance, we had a figure skater, ballerina, or whatever, and they were spinning with their, let's say their arms were, extended from their center of mass. Their moment of inertia will be a function of how far away their arms are from their center of mass. So when they bring their arms in, the moment of inertia changes, it gets smaller. So in the final case, so like let's say the beginning case, stick figure or whatever, okay. So we have, they're spinning around, their center of mass here at omega. So they have some initial angular momentum, but then when they bring their arms in, and this moment of inertia is going to be a function of the distance the arms away from the center of mass. So in the final case, the arms are brought in, okay? Then we have a change in the moment of inertia. The moment of inertia is going to get smaller because the radius is going to decrease. The arms are going to be brought closer to the center of mass. And so therefore, as a result, the final angular momentum is going to it's going to change, but the amount between both is going to be the same. So what we have here, and this is kind of like an illustration of why ballerinas spin faster when they bring their arms in. So if we just take this equation here, I omega I equals IF omega final, we see that this divided by this gives us a new angular velocity. The angular velocity is going to go up because the final angular moment or moment of inertia goes down. And the moment of inertia goes down here because their arms are brought in, the radius decreases. So if this goes down, the final angular speed goes up and they spin faster in place. So that's just an application of the conservation of angular momentum between the first case when they're spinning with their arms out and they bring their arms in. It's going to be the same. It's going to be the same value of angular momentum, but the angular speeds change as a result. So if this was, let's say that this was 2, angular momentum here, first case 2 times 1, and then, this is going to be 1 times 2. So the angular velocity is going to increase. So just a quick example on that. So the same amount, but the speeds do change relative to the moment of inertia. Okay, so let's keep that moving. So conservation principles we've seen so far. So let's see, let me do it this way. So we know that energy is saved before and after for no energy transfers. And we usually get energy transfer if there's friction in the system. And then momentum is saved. No outside forces. And then we get angular momentum saved for no outside torques. And these only work if the system is isolated. Close it off, spinning objects, and then this hits another one here, right? So this would be omega final, omega initial. Close it out from outside torques. And we save the angular momentum. Similar to if we had any number of objects closed from the environment hitting each other, the momentum is saved because we don't have any outside forces. All right, let's do an example from chapter 11. First example there. I'm going to do example 11.7. Formation of a neutron star, page 322. Okay, so we have this. A star rotates with a period of 30 days about an axis through its center. After the star undergoes a supernova explosion, the stellar core, which had a radius of 1 × 10⁴ kilometers, collapses into a neutron star radius 3 kilometers. Determine the period of rotation of the neutron star. So a way that you can determine what's going in the beginning and the end for angular momentum problems is there's always going to be 2 radii. In this case, we had a radius of the star first, and then it collapses. That would be the equal sign, the action that takes place, and then it collapses to a new radius, R1 to R2. So R1 deals with the initial angular momentum. The second radius deals with the final angular momentum. You can always think about it in terms of the new angular velocities. There's going to be a certain spin in the beginning, and then it collapses, and then there's going to be a new spin in the end. Much like you were dealing with when you were looking at your conservation of momentum problems, where you had an initial velocity, action takes place, final velocity. So a number of ways to think about where the beginning action takes place in angular momentum problems and where the final action takes place. So, initial to final, it's all, always going to involve, radii. And you'll see that as a common theme. Example 11.7, 11.8, and any of your angular momentum problems. Okay, so this star rotates with a period T of 30 days. Just repeating what's there, a little commentary. So the initial radius is 1 times 10 to the 4th kilometers. Final radius is 3 kilometers. So extend that. So again, step 1. So this star is spinning in 2 states, 2 radii. First radius, initial angular momentum. Second radius, final angular momentum. Okay, so conservation of angular momentum problem. And one caveat they have here, don't know what kind of shape this neutron star is. Assume it's a sphere for the most part, but since they're being technical about it, they're going to say that the moment of inertia is multiplied by some constant k. We don't know if it's 2/5, 1/2, 7/8, some constant. So they're just making a assumption that they don't know what the mass distribution is like. They don't know what type. They don't know what type of shape it is. So don't know the mass distribution, but we know that moment of inertia is always mr squared multiplied by some constant, and this constant, call it k. Usually you'll be given the shape. It's a cylinder, a sphere, so you know what moment of inertia to put there. And this kmr squared is going to go for the beginning and the end. So for the initial radius and the final radius. So again, using this formula here, we'll just put in our terms. And then omega, they show you that omega is 2 pi over t, where you really get that into the wave chapters. But here's how you can come up with omega being 2 pi over t. You know that this omega is v over r. And we also know that for objects that are spinning about, that the velocity is going to be equal to 2 pi r divided by t. So now if we take this and divide that by another r, which we have there, the omega, which this is, becomes 2 pi over t. That's how you get that. So it's going to be 2 pi over, the initial period, which is 30 days, so ti. And then that equals km r final squared, 2 pi over t final for the final case. And we're trying to look for the final period. So these km's cancel. And then if I move my tf over here, and then do my, these two pi's cancel out. So I'm just going to get this expression here, Rf over Ri squared times initial period, put in your numbers, and you can find the rotation period of a neutron star after it collapses from basically 10,000 kilometers down to 3. I'll infer that that's going to be a very quick period. So the final radius, 3 kilometers over 1 times 10 to the 4th. And then that's squared. Multiply that by the period 30. (2.7 times 10 to the minus 6 days). And that comes out to be, if you want to convert it to seconds, 0.23 seconds. So this neutron star rotates once every quarter of a second. Pretty tremendous. So it makes some physical sense. The radius is very small, ballerina, it's going to spin faster. But in this case, given all the initial parameters, this is pretty fast rotation period. Any questions on that example? I'm going to set up a final one and have you guys work on that. Just some additional questions. With this next example. Next example, page 319. Example 11.6. The seesaw problem. So we have this father on one side, daughter on the other, seesaw. Let's see. We have father of mass, m sub f, mass of father. M sub d. Rod of mass m, and it's got a length L. Okay. So it looks something like this. Center of mass. Daughter here. And then L. All right. So the question asks us to find the expression for the magnitude of the system's angular momentum. Since this is made up of point masses, well, we're going to use the angular momentum equation for the point masses, right? We're going to add all their angular momentum together to get the total angular momentum. So instead of using this guy, I omega, because it's not a actual shape, it's made up of 3 point masses, we can use, we're basically going to do we're basically going to do this, but we can come about it a different way. We can use their masses and their distances. So we're going to say the total angular momentum is going to just be made up of the individual angular momenta, which is equal to I omega. All right. So, so effectively, we can just, so yeah, we look at the, get the moments of inertia, multiply them by omega, and we're good. Either method is good. So the moment of inertia of the rod about the center of mass is going to be 1/12 ml squared. Just look that up from the table. The moment of inertia of the father is going to be the mass of the father times his distance away from the center, which squared, which is going to be L/2 squared. And then the daughter, same thing, mass of daughter, L/2 squared. So of course, the total moment of inertia just be the sum of all those. And so I have the rod, the father, and the daughter. 1/12 ml squared plus L squared over 4. And then the daughter plus L squared over 4. And then multiply that by omega. That's going to give you your total angular momentum. So let me just go back there. If we had a tangential speed, then yes, we could use MVR. So forgot we didn't have a tangential velocity here. So this is the most effective to get the right, is get the moments of inertia, add them, and then multiply it by this arbitrary omega, and we're good. So yeah. So L equals I total omega. And that's just going to be L squared over 4. Now we just factor out this L squared over 4 business, and M over 3, because that'll be, 1/12 ml squared there, and then mass of father, mass of daughter, squeeze in the omega there. And so that's our expression that we get. And so then for part A, and then for part B, they want you to find the angular acceleration, get an expression for that. Let's see. No, you're thinking torque. So the moment of inertia is just mass, so scalar. Okay, so we're going to do that we'll get into your question in part B. So I'm going to find the expression for angular acceleration alpha. So on the extreme edges of this seesaw, each of those masses is going to apply its own net torque. It's not going to be balanced, so net torque is not going to equal to 0. It's going to be equal to I times alpha, this expression, because there's a rotation, even if it's quarter rotation or whatever, there's something happening. So we only get an expression for alpha, which is going to be net torque over the moment of inertia that we calculated in part A. So our job in part B, as you can see, is just to get the net torque expression, and that'll be it. So again, the same picture. Let's try to move this over here. Okay. So I draw it in terms of torques, right? So we have full picture theta, and so we have the weight of the daughter here, and then weight of the father. And so it's going to be the torque about the rotation point. So the center of mass of the rod exerts no torque because it's at the hinge, the rotation point. So the torque of the father and the daughter, they apply torques. So if we're just looking at the father here, he's going to be applying a clockwise or counterclockwise torque, because if you just look at this force here is going to cause the system to rotate this way, counterclockwise. And conversely, the daughter will have a clockwise torque, so that's going to be a negative torque. So the torque by the father will be the force of the father, or the weight, times the distance away from the pivot. And we have to take a look at this force, which is his weight, and what it's perpendicular to. Okay, so if we're just looking at this full picture, the weight of the father here is going to be perpendicular to L cosine of theta. So this whole rod here is L, and then this will be L cosine theta. So the torque is going to be force times this radius, L cosine theta, L over 2, because the whole thing is L, so it's going to be L over 2 because he's half the distance, L over 2 cosine theta. That torque is coming out of the page or counterclockwise, and the torque by the daughter is going to be weight of daughter, L over 2 cosine theta. Put that into your net torque expression. So I'm going to cut out the middleman algebra there. You can see that in the text, but we're just adding these two expressions. GL cos theta. Okay. And so then alpha is just going to be this net torque expression divided by the moment of inertia we found in part A. And that comes out to be cos theta over 1/2 m over 3. So again, yeah, that's what we saw earlier. 3 plus mf md omega. So we saw that I was 1/4, and so this this net torque here being in terms of 1/2. When we do the math here, we want to get this expression to be 1/2 on the denominator. But then we can do something even better, get rid of the 1/2 on the denominator, and that becomes 2 mf minus md GL cos theta over and so that would be our arbitrary expression for alpha. Yeah, it becomes 1/2. Exactly. So it's just an algebra step that I waved my hand at because I knew you guys were efficient at that. But it doesn't matter. You make L capital or lowercase, same thing. So that would be our expression for the angular acceleration. Any questions on how other questions I got, how I get that angular acceleration expression? So. The omega is at the bottom, right here. Mhm. All right. So now given this expression for alpha, and we had, let's look back at the example. Let's take 10 minutes or so to find expressions for the linear acceleration or tangential acceleration. The time it takes to rotate let's see, to do 1/4 of a rotation. And let's find the center of gravity, which is the same thing, center of mass. Probably go back to chapter 9.5 for the formula for that, but to find the center of gravity with respect to all masses. So guys gonna stay there and work these expressions out in maybe 15 minutes.